Hello, judges. My project number is 700 ENMSH, and today I will be presenting increasing electromagnetic coil field strength through layering and material composition. The problem is that electromagnetic rails as a simple model are becoming inadequate by design, as they are less complex and costly, but do not create a high enough electromagnetic field to be used in energy applications such as nuclear fusion. Electromagnetic coils designs are being investigated increasingly for the purpose of creating stronger magnetic fields, as the current designs are insufficient to support future design goals. My project from last year included an improved electrical flow through the wire of the electromagnet with gauge and length improvements, while this year designs for the electromagnetic coils were tested so that an efficient and scalable model could be made to increase the distance traveled of the projectile to mimic the acceleration of tritium and deuterium in nuclear fusion, increasing the total field strength of the electromagnetic coil design by increasing the layers of the electromagnetic coil and improving the magnetic strength of the projectile with alternative ferromagnetic materials. Through my research, I found that nuclear fusion reactors use large electromagnetic coils in the most popular models, including the tokamak, which uses a torus shape to accelerate tritium and deuterium to the point where plasmas formed in the nuclei of these two isotopes form into a single nucleus, which is known as nuclear fusion. These nuclear fusion reactors would be able to generate a seemingly endless supply of clean, renewable energy if ignition, when more energy is provided than put into the reaction, is met, which is seeming more realistic as research and experimenting continues. Coils are more efficient than rails in an electromagnetic model due to their ability to create a much stronger electromagnetic field, with the con of being more complex. I chose the projectile materials of iron, cobalt, and nickel for their qualities of being the most ferromagnetic elements, meaning that they are the best at being attracted by magnetic forces. I chose 1, 2, and 3 layers of coil this year due to the past results of an increasing gauge causing the model to become less efficient from its increased volume for the electricity flow through. This model of electromagnetic coil activates to attract the projectile to the center, but then is released to be propelled in a forward motion. To implement my design goal, I increased the field strength of the electromagnetic coil design by increasing the layers of the electromagnetic coil and improving the magnetic strength of the projectile with alternative ferromagnetic materials. While using the most efficient model for my project last year as the control, the electricity would more easily flow through the larger amounts of electromagnetic coils rather than larger gauge of coil. The number of coils will cause a greater distance due to the increase in the number of magnetic field lines. With this better use of volume compared to an increase in gauge, along with the iron projectile, which allows for the greatest attraction to the electromagnetic field, the distance the projectile is propelled will be the greatest, with the model using 3 layers and an iron projectile. A complete materials list can be found in the research plan. A detailed procedure can be found in the research plan, and an image representing the materials used in my project can be found on the right. A video of my project can be seen here. This first graph represents the distance that an iron projectile is propelled over 10 trials, and it found that the distance propelled increases as the number of layers increases in the iron projectile, with a maximum average of 426 centimeters. This next graph represents the distance that a cobalt projectile is propelled over 10 trials, and it found that the distance propelled increases as the number of layers increases in the cobalt projectile, with a maximum average of 320 centimeters. This graph represents the distance that a nickel projectile is propelled over 10 trials, and it shows that the distance propelled increases as the number of layers increases in the nickel projectile, with a maximum average of 145 centimeters. This final graph represents a comparison of the average distances propelled by layers and projectile material in centimeters. It shows that 3 layers in green performs greater than 2 layers in yellow and 1 layer in red, and iron performs greater than cobalt, which performs greater than nickel. To analyze the data, The length that the projectile has traveled from the end of the coil system to the end of the projectile was measured in centimeters. 10 trials for each of the 3 different projectile materials and 3 numbers of layers showed that iron is the most efficient projectile material in terms of practicality as well as cost, as it propelled an average of 425 centimeters over 319.6 and 145.4 by cobalt and nickel respectively. There is, however, some variability within trials due to a reliance on a press button rather than a system that can release the projectile exactly when it reaches the center of the coil. An increase in the number of coil layers always leads to an increase in the projectile distance, and an iron projectile is seen to perform the greatest due to its increased level of attractivity to the magnetic forces, and 3 layers of coil perform the greatest due to its increase in the number of field lines and allowing the electricity to flow easily while increasing the volume, unlike an increase in gauge, which causes less field lines to be formed. In conclusion, the data supported the hypothesis in that an increase in number of layers strengthened the electromagnetic field, and the iron projectile traveled the greatest average distance propelled of 425.9 over 319.6 and 145.4, respectively, for the cobalt and nickel projectiles. The largest application of a scalable model of electromagnetic coil can be seen in many popular models of nuclear fusion reactors for the purpose of creating large quantities of clean and renewable energy. These reactors use large electromagnetic coils to accelerate tritium and deuterium to the point where plasma is formed and contained in a torus-shaped container to be efficiently converted into energy to be stored. Some recommendations that I have for this project include testing different materials to be used in the coil itself, such as the use of superconductors, and a more realistic test for the use of nuclear fusion could be done instead of testing for the field strength of the electromagnetic coil itself. A complete bibliography can be found in the research plan. Thank you, judges, for viewing my video.